Nonlinear optics is the branch of optics that describes the behavior of light in nonlinear media, that is, media in which the dielectric polarization P responds nonlinearly to the electric field E of the light. This nonlinearity is typically only observed at very high light intensities such as those provided by lasers. Above the Schwinger limit, the vacuum itself is expected to become nonlinear. In nonlinear optics, the superposition principle no longer holds. Nonlinear optics remained unexplored until the discovery in 1961 of second harmonic generation by Peter Franken al. at University of Michigan, shortly after the construction of the first laser by Theodore Harold Mayman. Nonlinear optical processes. Nonlinear optics explains nonlinear response of properties such as frequency, polarization, phase or path of incident light. These nonlinear interactions give rise to a host of optical phenomena. Frequency mixing processes, second harmonic generation, or frequency doubling, generation of light with a doubled frequency. Two photons are destroyed, creating a single photon at 2 times the frequency. Third harmonic generation, generation of light with a tripled frequency. 3 photons are destroyed, creating a single photon at 3 times the frequency. High harmonic generation, generation of light with frequencies much greater than the original. Sum frequency generation, generation of light with a frequency that is the sum of 2 other frequencies. Difference frequency generation, generation of light with a frequency that is the difference between 2 other frequencies. Optical parametric amplification, amplification of a signal input in the presence of the higher frequency pump wave, at the same time generating an idler wave. Optical parametric oscillation, generation of a signal an idler wave using a parametric amplifier in a resonator. Optical parametric generation, like parametric oscillation but without a resonator, using a very high gain instead. Spontaneous parametric down conversion, the amplification of the vacuum fluctuations in the low-gain regime. Optical rectification, generation of quasi-static electric fields. Nonlinear light-matter interaction with free electrons and plasmas. Other nonlinear processes: optical Kerr effect, intensity-dependent refractive index self-focusing, an effect due to the optical Kerr effect caused by the spatial variation in the intensity creating a spatial variation in the refractive index. Kerr lens mode locking, the use of self-focusing as a mechanism to mode lock laser cell phase modulation, an effect due to the optical Kerr effect caused by the temporal variation in the intensity creating a temporal variation in the refractive index. Optical solitons, an equilibrium solution for either an optical pulse or spatial mode that does not change during propagation due to a balance between dispersion and the Kerr effect. Cross-phase modulation, four-wave mixing, can also arise from other nonlinearities. Cross-polarized wave generation, effect in which a wave with polarization vector perpendicular to the input one is generated. Modulational instability, Raman amplification, optical phase conjugation, stimulated Brillouin scattering, interaction of photons with acoustic phonons. Multiphoton absorption, simultaneous absorption of 2 or more photons, transferring the energy to a single electron. Multiple photoionization, near simultaneous removal of many bound electrons by one photon. Chaos in optical systems. Related processes. In these processes, the medium has a linear response to the light, but the properties of the medium are affected by other causes. Pockels effect, the refractive index is affected by a static electric field, used in electro-optic modulators. Acousto-optics, the refractive index is affected by acoustic waves, used in acousto-optic modulators. Raman scattering, interaction of photons with optical phonons. Parametric processes. Nonlinear effects fall into 2 qualitatively different categories, parametric and non-parametric effects. A parametric nonlinearity is an interaction in which the quantum state of the nonlinear material is not changed by the interaction with the optical field. As a consequence of this, the process is instantaneous, energy and momentum conserving in the optical field, making phase matching important, and polarization dependent. Theory: parametric and instantaneous nonlinear optical phenomena, in which the optical fields are not too large, can be described by a Taylor series expansion of the dielectric polarization density P at time t in terms of the electrical field E. Here, the coefficients chi are the nth order susceptibilities of the medium, and the presence of such a term is generally referred to as an nth order nonlinearity. Note that the polarization density P and electrical field E are considered as scalar for simplicity. In general, chi is an n+1 order tensor representing both the polarization-dependent nature of the parametric interaction as well as the symmetries of the nonlinear material. Wave equation in a nonlinear material. Central to the study of electromagnetic waves is the wave equation. Starting with Maxwell's equations in an isotropic space containing no free charge, it can be shown that where Pnl is the nonlinear part of the polarization density and n is the refractive index which comes from the linear term in P. Note: one can normally use the vector identity and Gauss's law to obtain the more familiar wave equation for nonlinear medium. Gauss's law does not imply that the identity is true in general, even for an isotropic medium. However, even when this term is not identically zero, it is often negligibly small and thus in practice is usually ignored, giving this the standard nonlinear wave equation. Nonlinearities is a wave mixing process. The nonlinear wave equation is an inhomogeneous differential equation. The general solution comes from the study of ordinary differential equations and can be solved by the use of a Green's function. Physically, one gets the normal electromagnetic wave solutions to the homogeneous part of the wave equation, and the inhomogeneous term acts as a driver, source of the electromagnetic waves. One of the consequences of this is a nonlinear interaction that will result in energy being mixed or coupled between different frequencies, which is often called a wave mixing. In general, an nth order will lead to n+1 th wave mixing. As an example, if we consider only a second-order nonlinearity, then the polarization P takes the form if we assume that E is made up of two components at frequencies ω1 and ω2. We can write E as n using Euler's formula to convert to exponentials where C stands for complex conjugate. Plugging this into the expression for P gives, which has frequency components at 2 ω1, 2 ω2, ω1 plus ω2, ω1 ω2, and 0. These three wave mixing processes correspond to the nonlinear effects known as second harmonic generation, sum frequency generation, difference frequency generation, and optical rectification respectively. Note: parametric generation and amplification is a variation of difference frequency generation, where the lower frequency of one of the two generating fields is much weaker or completely absent. In the latter case, the fundamental quantum mechanical uncertainty in the electric field initiates the process. Phase matching the above ignores the position dependence of the electrical fields. In a typical situation, the electrical fields are traveling waves described by a position with the wave vector, whereas the velocity of light in vacuum is the index of refraction of the medium at angular frequency. Thus, the second-order polarization at angular frequency is at each position within the nonlinear medium. The oscillating second-order polarization radiates at angular frequency in a corresponding wave vector. Constructive interference, and therefore a high-intensity field, will occur only if the above equation is known as the phase matching condition. Typically, three-wave mixing is done in a birefringent crystalline material, where the polarizations of the fields and the orientation of the crystal are chosen such that the phase matching condition is fulfilled. This phase matching technique is called angle tuning. Typically a crystal has three axes, one or two of which have a different refractive index than the other one. Uniaxial crystals, for example, have a single preferred axis, called the extraordinary axis, while the other two are ordinary axes. There are several schemes of choosing the polarizations for this crystal type. If the signal and idler have the same polarization, it is called type 1 phase matching, and if their polarizations are perpendicular, it is called type 2 phase matching. However, other conventions exist that specify further which frequency has what polarization relative to the crystal axis. These types are listed below, with the convention that the signal wavelength is shorter than the idler wavelength. Most common nonlinear crystals are negative uniaxial, which means that the E-axis has a smaller refractive index than the O-axis. In those crystals, type 1 and 2 phase matching are usually the most suitable schemes. In positive uniaxial crystals, types 7 and 8 are more suitable. Types 2 and 3 are essentially equivalent, except that the names of signal and idler are swapped where the signal has a longer wavelength than the idler. For this reason, they are sometimes called IIA and IIB. The type numbers V8 are less common than I and 2 and variants. One undesirable effect of angle tuning is that the optical frequencies involved do not propagate collinearly with each other. This is due to the fact that the extraordinary wave propagating through a birefringent crystal possesses a Poynting vector that is not parallel with the propagation vector. This would lead to B-Markov, which limits the nonlinear optical conversion efficiency. Two other methods of phase matching avoids B-Markov by forcing all frequencies to propagate at a 90-degree angle with respect to the optical axis of the crystal. These methods are called temperature tuning and quasi-phase matching. Temperature tuning is where the pump frequency polarization is orthogonal to the signal and idler frequency polarization. The birefringence in some crystals, in particular lithium niobate, is highly temperature dependent. The crystal is controlled at a certain temperature to achieve phase matching conditions. The other method is quasi-phase matching. In this method the frequencies involved are not constantly locked in phase with each other. Instead, the crystal axis is flipped at a regular interval lambda, typically 15 micrometers in length. Hence, these crystals are called periodically poled. This results in the polarization response of the crystal to be shifted back in phase with the pump beam by reversing the nonlinear susceptibility. This allows net positive energy flow from the pump into the signal and idler frequencies. In this case, the crystal itself provides the additional wave vector k equals 2 pi lambda to satisfy the phase matching condition. Quasi-phase matching can be expanded to chirped gratings to get more bandwidth into shape an SHG pulse like it is done in a dazzler. SHG of a pump and cell phase modulation of the signal in an optical parametric amplifier can be integrated monolithically. Higher order frequency mixing. The above holds for processes. It can be extended for processes where is non-zero, something that is generally true in any medium without any symmetry restrictions, in particular resonantly enhanced sum or difference frequency. Mixing in gases is frequently used for extreme or vacuum, ultraviolet light generation. In common scenarios, such as mixing in dilute gases, the nonlinearity is weak and so the light beams are focused, which, unlike the plane wave approximation used above, introduces a pi phase shift on each light beam, complicating the phase matching requirements. Conveniently, difference frequency mixing with cancels this focal phase shift and often has a nearly self-canceling overall phase matching condition, which relatively simplifies broad wavelength tuning compared to some frequency generation. In all four frequencies are mixing simultaneously, as opposed to sequential mixing via two processes. The Kerr effect can be described as a as well. At high peak powers, the Kerr effect can cause filamentation of light in air, in which the light travels without dispersion or divergence in a self-generated waveguide. At even high intensities, the Taylor series, which led the domination of the lower orders, does not converge anymore, and instead a time-based model is used. When a noble gas atom is hit by an intense laser pulse, which has an electric field strength comparable to the Coulomb field of the atom, the outermost electron may be ionized from the atom. Once freed, the electron can be accelerated by the electric field of the light, first moving away from the ion, then back toward it as the field changes direction. The electron may then recombine with the ion, releasing its energy in the form of a photon. The light is emitted at every peak of the laser light field, which is intense enough, producing a series of attosecond light flashes. The photon energies generated by this process can extend past the 800th harmonic order up to a few keV. This is called high-order harmonic generation. The laser must be linearly polarized, so that the electron returns to the vicinity of the parent ion. High-order harmonic generation has been observed in noble gas jets, cells, and gas-filled capillary waveguides.